An open delta transformer configuration, typically utilizing two transformers, such as a 10 kVA and a 15 kVA transformer to supply a 120/240 volt three-phase system, presents specific considerations for load connections. It's crucial to understand the voltage characteristics at different points within this open delta configuration. The 240 volt single-phase supply within this open delta system is derived from the windings of the transformers. One must identify the legitimate connection points for safely drawing 240 volt single-phase power. Attempting to connect a 240 volt single-phase load to the open side of the delta is not permissible. The open side of the delta configuration is precisely that, an open circuit. It's a point where a transformer winding is intentionally absent to create the three-phase relationship using only two transformers. There is no electrical potential or voltage present at this open point, as it is not connected to any energized transformer winding. Therefore, any load connected to this open point will effectively be connected to nothing, and it will not receive any power. Connecting a load in this manner is electrically unsound and potentially dangerous. It's essential to consider the voltage and current limitations of the transformers used in the open delta bank. The 10 kVA and 15 kVA ratings define the apparent power each transformer can deliver without exceeding its design limit. When connecting single-phase loads to the appropriate terminals of the transformer windings, one must ensure that the load does not exceed the capacity of the individual transformer to which it is connected. Overloading a transformer can lead to overheating, insulation breakdown, and premature failure. Single-phase load should be connected between the identified phase legs and the neutral, or between two phase legs if a 240 volt single-phase load is required and available through the transformer winding connections. The center tap on one of the transformers provides the neutral point for the 120 volt system. Loads must be balanced as much as possible across the available phases to prevent excessive current flow in any one transformer, which can lead to overheating and reduced efficiency. It's important to consult relevant electrical codes and standards, such as the National Electrical Code, or NEC, for specific requirements related to transformer installations and load connections. The NEC provides guidelines for conductor sizing, overcurrent protection, grounding, and other safety considerations. It's essential to comply with these codes to ensure a safe and reliable electrical installation. The NEC addresses transformer installations in Article 450. This article covers requirements for overcurrent protection, grounding, ventilation, and other safety aspects. The specific requirements vary depending on the transformer size, location, and application. Overcurrent protection is crucial to protect transformers from overload and short-circuit conditions. The NEC specifies the maximum overcurrent protection allowed for transformers based on their rated current. Typically, the primary overcurrent protection is sized no larger than 125% of the transformer's primary current rating. The secondary overcurrent protection is sized based on the secondary conductor's ampacity. Grounding is also essential for safety. Transformers must be properly grounded to provide a low impedance path for fault currents, which helps to prevent electric shock hazards. The NEC specifies the grounding requirements for transformers, including the size and type of grounding conductors. Ventilation is also important to prevent overheating. Transformers generate heat during operation, and adequate ventilation is necessary to dissipate this heat. The NEC specifies the ventilation requirements for transformers, which vary depending on the transformer size and location. In addition to the NEC, other standards may also apply to transformer installations. These standards may include those published by organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA. These standards provide detailed guidance on transformer design, testing, and application. It's also important to consider the specific requirements of the local electrical utility. The utility may have additional requirements for transformer installations that must be followed. These requirements may include restrictions on the size and type of transformers that can be installed, as well as requirements for metering and protection. Open delta transformer configurations present unique challenges compared to closed delta or Y-connected systems. The reduced transformer capacity and potential for imbalanced voltages and currents must be carefully considered when designing and installing open delta systems. A qualified electrician should always perform electrical work, ensuring compliance with all applicable codes and standards. Electrical work can be dangerous if not performed correctly. Only qualified personnel should work on electrical systems. The open delta configuration is commonly used when a three-phase power supply is needed but the full capacity of a closed delta or Y-connected system is not required, or when initial costs are a major concern. It provides a more economical solution in these situations, but it's important to understand its limitations. The open delta configuration provides only 57.7% of the capacity of a fully rated delta system using 3 identical transformers. This means that the 2 transformers in an open delta configuration must be sized accordingly to meet the load requirements. Also, the open delta system is more susceptible to voltage imbalance than a closed delta system. This means that the voltages on the 3 phases may not be equal, which can affect the performance of sensitive equipment. Careful load balancing is essential in open delta systems to minimize voltage imbalance. The impedance characteristics of the transformers in the open delta configuration also play a role in the overall system performance. The impedance of the transformers affects the voltage regulation and short-circuit current levels in the system. It's important to select transformers with appropriate impedance characteristics for the application. When troubleshooting an open delta system, it's essential to use a systematic approach. Start by verifying the incoming voltage and phase rotation. Then check the transformer connections and the load connections. Use a multimeter to measure voltages and currents at various points in the system. If a problem is identified, isolate the faulty component and replace it. Always follow proper safety procedures when working on electrical systems. Wear appropriate personal protective equipment, or PPE, such as gloves and safety glasses, to energize the circuit before working on it whenever possible. Use a voltage tester to verify that the circuit is de-energized. If you are not comfortable working on electrical systems, hire a qualified electrician. Understanding the principles of operation, installation requirements, and safety considerations associated with open delta transformer configurations is crucial for ensuring a safe and reliable electrical system. Consulting with qualified professionals and adhering to applicable codes and standards is essential for successful implementation. The primary disadvantage of an open delta transformer bank, as compared to a closed or 3 transformer delta bank, is its reduced capacity. An open delta bank can only supply 57.7% of the kVA that a fully rated 3 transformer delta bank can supply. For example, 250 kVA transformers in an open delta configuration can only supply approximately 86.6 kVA, not 100 kVA. Firstly, calculate the total kVA of a closed delta bank with 3 identical transformers. You would add the kVA ratings of each transformer to find the total. Secondly, with an open delta bank, the total kVA is not simply the sum of the 2 transformer kVA ratings. It is the square root of 3 multiplied by the kVA rating of one of the transformers if they are the same size. Alternatively, you can calculate it as 57.7% of the kVA of a fully rated 3 transformer delta bank using the same transformer size. Thirdly, an open delta bank is more susceptible to voltage imbalance than a closed delta bank. This can occur if the loads on the 3 phases are not balanced. This imbalance can cause problems with sensitive electronic equipment. The impact of voltage imbalance on equipment depends on the severity and duration of the imbalance. Slight imbalances may have little to no noticeable effect. More significant imbalances can cause motors to overheat, reduce their efficiency, and shorten their lifespan. Sensitive electronic equipment may malfunction or be damaged by voltage imbalance. Measuring voltage imbalance is a straightforward process using a multimeter capable of measuring AC voltages. Firstly, measure the voltage between each phase and a neutral point, if available, or between each pair of phases if a neutral is not accessible. This will give you 3 voltage readings. Secondly, calculate the average of the 3 voltage readings you obtained. Thirdly, determine the deviation of each individual voltage reading from the average voltage. Find the largest of these deviations. Fourthly, calculate the percentage voltage imbalance by dividing the maximum voltage deviation by the average voltage and multiplying by 100. The resulting percentage represents the voltage imbalance in the system. Regular monitoring of voltage imbalance can help identify potential problems early on, allowing for corrective actions to be taken before equipment is damaged. If the calculated voltage imbalance exceeds acceptable limits, corrective actions should be taken to mitigate the imbalance. There are several ways to mitigate voltage imbalance in an open delta system. Firstly, try to balance the loads in the three phases. This will help to reduce the amount of current flowing through each transformer. Secondly, you can install a voltage regulator. A voltage regulator will help to maintain a constant voltage on the three phases, even if the loads are unbalanced. Thirdly, you can replace the open delta bank with a closed delta bank. A closed delta bank is less susceptible to voltage imbalance. The cost of the transformers is one of the main economic considerations in open delta vs closed delta transformer configurations. An open delta requires only 2 transformers instead of 3, which can result in lower initial costs. However, this cost saving must be weighed against the reduced capacity and increased susceptibility to voltage imbalance. The physical space constraints for the transformer installation can also be a factor. In situations where space is limited, the open delta configuration may be a better option, as it requires less space than a closed delta configuration. The potential for future load growth should also be considered. If there is a possibility that the load will increase in the future, it may be worthwhile to install a closed delta bank initially, even if it is not fully utilized. This will provide more capacity for future expansion. The reliability requirements of the application should also be considered. An open delta bank is more susceptible to outages than a closed delta bank. If a transformer in an open delta bank fails, the entire system will be out of service. The available utility infrastructure can also influence the choice between open delta and closed delta configurations. In some cases, the utility may only provide a certain type of service, which may limit the options available. The local electrical codes and regulations may also have specific requirements for transformer installations. It's essential to comply with all applicable codes and regulations to ensure a safe and code-compliant installation. Maintenance requirements should also be factored into the decision-making process. Regular inspection and maintenance are essential for ensuring the reliable operation of transformers. The type of loads served by the transformer bank can also influence the choice between open delta and closed delta configurations. Some loads, such as motors, are more sensitive to voltage imbalance than others. The voltage regulation requirements of the application should also be considered. Voltage regulation refers to the ability of the transformer bank to maintain a constant voltage under varying load conditions. The harmonic content of the loads can also affect the performance of the transformer bank. Harmonics are distortions of the voltage and current waveforms that can cause overheating and other problems. The ambient temperature and altitude at the installation site can also affect the transformer's performance. Transformers are typically rated for operation at a specific ambient temperature and altitude. Exceeding these ratings can reduce the transformer's lifespan. Open delta configurations require careful consideration of these factors to ensure that the chosen configuration meets the specific needs of the application. A comprehensive engineering analysis should be performed to evaluate all relevant factors and select the optimal transformer configuration. Furthermore, regular inspection and maintenance of the transformers are essential for ensuring their continued reliable operation. This includes checking for signs of overheating, corrosion, and other damage. Testing the insulation resistance of the transformer windings is also a good practice. Insulation resistance testing can help identify potential insulation problems before they lead to a failure. Furthermore, thermal imaging can be used to detect hot spots on the transformer surface, which can indicate problems with the cooling system or internal connections. It's important to keep the transformer enclosure clean and free of debris. Debris can obstruct ventilation and cause overheating. Also, ensure that the transformer bushings are clean and properly tightened. Loose or corroded bushings can cause arcing and insulation failure. The transformer's oil level should also be checked regularly if it's an oil-filled transformer. Low oil levels can indicate a leak, which should be investigated and repaired promptly. If the transformer has a low tap changer, it should be inspected and maintained according to the manufacturer's instructions. Low tap changers are used to adjust the transformer's voltage ratio under load. In addition to regular maintenance, it's also important to keep accurate records of all inspections and maintenance activities. These records can be helpful for troubleshooting problems and tracking the transformer's performance over time. The lifespan of a transformer depends on a variety of factors, including the design and quality of the transformer, the operating conditions, and the maintenance practices. With proper maintenance, a transformer can last for many years. The cost of replacing a transformer can be significant, so it's important to take steps to extend its lifespan. The open delta transformer configuration provides a cost-effective solution for providing three-phase power in situations where the full capacity of a closed delta system is not required. Firstly, ensure all connections are tight. Secondly, balance the load as much as possible. Thirdly, implement a routine inspection program. Regular inspections and maintenance can help identify potential problems before they lead to failures.